So let's come back. So first of all, let me clarify. Actually, this example 2 is not about like actually process A and process B. In this example, there are different processes. So actually, what I'm referring is about if process A forks process B. Actually, the file descriptor table will be the same, will be totally the same if process A forks process B. Okay, but in this example, I'm just going to show you for FD2, because for FD2 here and FD2 here, they point to the same open file table. There are several reasons to lead to this kind of result, but one of the most general way is about to use fork. Okay, so example 2 here and process A and process B here, I would say it's not really the same things, because now process A, the file descriptor for process A is not the same as process B. So in this example on the right hand side now, it's not about process A forks process B. Okay, but because I have no room to draw another figure here, so for example 2, you can think about actually when there are two file descriptor, they point to the same open file table. One possible and general reasons is about maybe it's because these two processes, they are fork relations. One parent fork the child, so their file descriptor point to the same open file table. Okay, so that is for the clarification. And okay, so for super block operations, actually it's going to perform the low-level operation on the file system and its inodes. So if a file system wants to write to its super block, actually it can like this. Super block point to the s dash operation, the pointer point to the super block, and then to write the like super block operation like this. So this is about here. You can use this. Sorry, one more time. So you can use this super block to point to the operations, and in the operations format, you can choose one of the functions you are going to run. And in this example, if we are going to write the super block, for example, to write something into this super block, then we will use this write dash super block functions. So it depends if you are going to delete inode or you are going to write an inode, then you will use this chain from the super block, get the super block operations and do the operations. Okay. And here are several things. The first one is about like allocate dash inode is to create and initialize a new inode object. And then destroy is about to deallocate. So the creations of inode actually depends on the file system. So it is from the super dash operations, we will do this kind of stuff. Okay. And here are dirty and write. So dirty and write, you can think about dirty is about when an inode is dirty. So you can use this function to do journal updates. Okay, what is journal updates? So dirty means like when there is a file and you move the file into a memory and you modify the file in the memory, and if you are going to write it back to the storage device, then one way is called journal. So we will write the new data from the memory back to the storage in the journal area, and this is how to manage this kind of dirty inode. Okay. So write dash inode is going to write a given inode to disk. Okay. And then delete inode is about just to delete a given inode from disk. Okay. So put dash super is going to code when unmounted to release the given super block. Okay. And this one, write dash super is to update the undate super block. So because these data structures, they are in the memory. So this super block data structure is in the memory. So when you call the super dash operation inside this write dash super, we can synchronize the modified information from the memory to the disk. So it is about the synchronization usage. Okay. Oh, one more time. Actually, like in your final exam, I mean, I will not really ask you about like what this function is about. I mean, actually, these functions here just want to let you know what superblock operations look like, just give you some feelings. So there will not be on your exams about to ask you about, for example, what is put dash super means and what is sing dash fs means. So the same things for all the rest of the like I know object operations, those kind of stuff. There will not be all on your text about what each of the meaning of each functions. Because I think this is too tedious. Okay, so that is for superblock. So the next one, I think the most important thing is the I know object. So I know object represents all the information needed by the kernel to manipulate a file. So this I know represents metadata of each file on the file system, and the I know object is constructed in memory only as files are accessed. So inode is usually on the disk, and I know object usually it is in the memory. Okay, so you can think about inode is a file backup version for the inode object. Okay, so here are several kind of inode operations. So this operation here is just want to let you feel about like what is inode objects, the rule. What is the rule of the inode objects? So like here we have a create. Create is to create a new inode associated with the D entry object with the access mode. So here are several parameters that you can use to create a new inode. And here is a kind of lookup. Lookup is quite important. I mean, we'll give a brief example about how lookup affects the file lookup. Okay. So lookup here actually is about to look up a certain file in this file directory tree. So we search a directory for an inode corresponding to a file name specified in the given D entries. So as you already know, file name is stored inside a D entry. So given the D entry, we can know the file name. And we will use the file name to trace the tree about to get where is the location of this file. So there will be an example later, like how to parse the absolute path to get to the end of this data. And also there is symbolic link, like creates a symbolic name link and names sim name to the file. So because when you are using a symbolic link, you can think about you are going to make a kind of extension from one file, right? So this shortcut, this extension, this shortcut, actually you can give it different names. It doesn't really need to be the same names as the original file. So the same things here, the SYM name here is just going to let you know, actually, when you are doing the shortcut, actually you can give it different names. Okay. Okay. So there is another thing is called remove directory. So one important thing to let you know is about, actually, even now we are talking about inode, but because we say in Linux, directory and inode, directory and file, they all use the inode, right? So inside the inode operation, actually, there is make directory and remove directory. So inode can control both the status of directory and file. So make directory, remove directory, and then rename, they're all about relationship between the directory part. Okay. So actually the rename function is very, I would say like, it's quite special for you guys like to know, because rename, maybe when we are using the Windows or like using the Linux, actually, if you are not using a command line, the rename is just about you really type the name of the file and you type a new name, right? But actually in the implementation of Linux, it is not really to directly modify the name inside the D entry. Because when you are using the command line, when you are going to rename a file in Linux, actually there is no rename function because you need to move the file from one name to another name, right? The way you are going to rename the file in Linux command line, you will use a mv instructions or like the mv command to move the file from one name to another name. Okay, so in Linux, actually, it moves the files specified by old entry from the like old dir directly to the new dir directly. So actually, to make it short, it is about we need to replace the old D entry by the new D entry. We are not going to directly modify the name inside the entry because there will be some consistent issues. And I have an animation later to let you know what would happen if we directly modify the name inside the entry. Okay. So the next one is the entry object. So the entry object is about the hierarchical nature of the file system. Like for this example, like we have a path like /home/hello/world, right? So actually we'll get all the entry objects /home, hello, and world. Okay, so actually when we are going to store this kind of information on disk, each of them we can receive a directory entry, right? But only using this directory entry, it will be time consuming to construct the path. So to read out this directory entry from the disk to the memory, actually we use another object called the entry object to quickly find out, to link out this path together. And then always can use this path, or like a virtual file system can use this path to quickly locate where is the data is. Then this one will give you an example about how to kind of parse this kind of path name and how to get the data out later. Okay, so I think this is also quite important. The VFS constructs the entry objects on the fly as needed when performing directory operations. So the entry object does not correspond to any sort of on-disk data structure. What does it mean? Like this. When we are talking about inode object, actually we said inode object, there is a file backup in the storage device, right? Because inside the storage there is inode table. So inside the inode table, we maintain both directory and file together. And inode object is going to describe those file and directory. But the entry is not the same things, because the entry is not going to describe how the data stored inside the storage device. The entry is about how to quickly find out the path. Given this path /home/hello/world, is it possible to quickly know where the location is without accessing the storage device? Okay, so the entry object is for the optimization for finding the data inside the memory, not from the storage. And we'll let you know later, like how does it work. So usually the entry object can be in one of the three states. The first one is the use state. So use state is corresponding to a valid inode and is owned by some users. I think this is quite common. Just like if there are some process and we're going to read out the data from the storage device. And of course, like when you are going to read out the data, you need to first parse the path name, right? You need to know where the data is. So you need to first parse the path and then get the data. So you need both the entry and then the inode object. Okay, so there is another state is called unused. So unused is about the entry corresponding to a valid inode. Again, for that data, there is a file path, but the thing is but it does not belong to any user. Maybe the users already released the file, but because those files are still in the patch cache or like in the memory. So for short benefit, for example, if maybe this file is a hard file. So in this case, we will choose not to directly release the entry objects at the moment the user released the file. So this is the things I say, it just cached there. In this unused state, no process use this kind of the entries. Okay. So there is another thing is called negative. So negative is not associated with inode. So either the inode was deleted or the path name was never correct. Okay, so this one is because even the path name is not correct or the inode was deleted, we still put the entry, we still put the path name inside the memory. Is because if one day there's another process open the same file, then in this case, we don't really need to reconstruct the path again. Because as we mentioned in the prior slides, the entry is just for the optimization for the fast accessing the file path. Okay, so for fast accessing a file path, it doesn't really need to be consistent with the storage device. Okay, so this is for the negative state. So both the entry objects and the corresponding inodes can be cached for faster directory lookup and file metadata access. Okay, and this one I'll give you one example later. So let's quickly look into what the entry objects look like. Okay, so actually this is the entry objects related kind of operations. So I'm just only to talk about the d-hash. So d-hash, it looks like to create a hash value from the given d entry. And the VFS codes this whenever it adds a d entry to the hash table. So like, because it is very time consuming if we are going to compare the entry one by one, right? Because the entry you can think about is a string. Then we are going to compare it. It takes a lot of time. And a better way is if we can hash the string to some hash number, then we can directly compare the hash number. We can know whether these two the entries is the same or not the same. So using hashing, we can quickly know like if the this the entry already exists in the memory or not. Okay, so this is I think this is the how hashing can benefit this kind of data finding things. And the rest of them, just like the entry release, the entry delete, or input like this, I will just skip it because I think it's not quite important. So okay, let me directly jump into the key things because I think I know the entry, it is not easy to understand. So let me use the rename to make you an example about how those kind of information look like. So in Linux, actually, rename function, it works like to replace the old the entry with a new one, having a new name. Okay. So I think there is a very intuitive question is about why not just directly modify the name in the D entry? Why we need to create a new D entry and replace the old one? It seems like it takes a further step to realize this rename process, rename function. But there are there are a lot of reasons, but just these two reasons, I think they are better to understand. The first one is consistency issue. And the reason is because updating a name directory directly is not atomic. So like this. So this is for reason one's example. So this figure is just like our prior slides. So in our storage device, there are several regions. One is for inode, and one is for data blocks, and one is for the data blocks, right? So inside the derivative entries, inside the derivative block, there are several derivative entries belonging to that directory. Okay, so these are all the same as the prior. So inside the memory, actually, you can see there is a D entry. So this D entry maintains about the information for file one's information. So because inside the D entry, there is a file name and there is an inode pointer. So this pointer will point it to the corresponding inode. So here, the inode object for the file one can use the inode pointer in the entry to get it. Okay, so inside the inode object, actually there are several information. So this is a stat. So stat means about if this file is updated or not. Is it a latest version? So if the stats say, hey, actually this is a dirty file, it means the file is updated. And it doesn't consist with the storage part. So it becomes dirty. So clean means like in the memory and the storage, the data is consistent. Okay. Then the second one is the file size. Okay. So because the file size, it varies. I mean, we don't really limit the size of the file. So some files is large, some files is small. So the inode will describe about the size, about how large it is. Okay. And oh, sorry, there's a typo here. This should be operations. But this operation, just like you already know, like inode operations. So we can use this operation to point to any kind of inode operations there that we are going to use. Okay. And then the last one I think is quite important is the data pointer, because this data pointer will point to the data in the page cache. Okay, so when we are going to access the file, in this example, this file is called file one. So file one will be moved. I mean, the data block of file one will be moved to the memory. and it will be placed in the region called patch cache. So you can see actually both data structure and patch cache, they all use the memory. Okay, but the difference is about like if we are going to get the data in the patch cache, then we need the pointer inside the inode object. So this inode object can help to point to where the data is stored in the memory. Okay. Oh, one another thing to let you know is actually in the inode in the storage device, there is also a pointer to point to the location inside the storage device. So in the inode object, the data pointer is pointing to the memory address. In the storage device, the inode is going to point to the block address inside the storage device. So this is quite different for these two data structure. Even they look very similar, but the pointer points to different place. Okay. Okay. So this one is just to let you have a big picture about like what is a D entry and inode, and then we are talking about patch cache at the end of this lecture. Okay, but probably maybe later or maybe next week. So okay, the thing is about if we are going to update the name for file one, so if we directly update the name in the D entry, then we need to do the next step is to update the name inside the directory entries, right? Because we update the name is inside the memory, but we still want the update to be shown inside the storage device. Otherwise, you shut down your computer and you reboot it, then the file name will be inconsistent. So we always need to sync with the data in the storage device. Okay, but the problem is here. If we are going to directly modify the file name, and when the virtual file system starts to write back the updated file name to the directory entries on the storage device. But if there is a power failure, then we will face the partial results inside the directory entries, right? Because for example, if the file one's name is quite long and maybe we only write several characters inside the directory entries, then we face a maybe system crash or power crash. Then in this case, the data, the new name inside the directory entries will be partial, and there will be an error. There will be an inconsistency here. And the reason is about when we are going to write the data in a storage device, it should take a super long time because storage device is so slow. So it makes these operations cannot be atomic. So atomic means about like these operations will not be affected by any crashes. Like we can make sure this operation is all or nothing. Either we can make the operation succeed or it will fail. Okay, but updating the name into the storage device is not atomic. I'll show you later what is called atomic. Okay, so a correct way is we will create a new D entries in the memory, and then we will give it a new name. So now files one's new name is here. And the inode pointer will still point to the same inode object because we do not really update the inode object here. We only update the name. And then we will write the entry back to the directory entries. Okay, we'll update the whole directory entries. And this can be an atomic operation because it can be all or nothing. Either we update successfully, otherwise we can roll back. Okay, we can roll back to the old version. Okay, because we will only we will create a new D entry, and then after we finish the creation, we will delete the prior one. Okay, so even there is a power failure, even we only write half of the new entry, it doesn't really matter. We can still roll back to the prior version. Okay, so there are only two steps. One is we do not really successfully update the name. Like we can use the prior old name, or we can use a new name. So there is no inconsistent state, or you can think about there is no unpredictable result. The result will only be success or failure. And if failure, you can use the old one. You can use the old name. But if you directly modify the file name here, if you directly modify file name, then there will be a ton of cases there because maybe you only write maybe only 2 words or maybe 3 words or 4 words. So you cannot predict the results if there is a failure there. Okay, so this is how atomic is so important for this kind of file system structure. So this is the first reason. And actually there is another reason here. So another reason is if the new name is longer than the old one, and there is no space in the block, how does it handle? So you can think about like this. For dirty entry on the store device, the structure looks like this. There is inode number, and the inode number will be 4 byte. And this is the static size for the inode numbers. Okay, so there is another thing called name-len. So this is 1 byte. Okay, so this is about to show how long is the len, how long is a name, because name is a variable things. For example, different files they have different length for the name. So we need to first know like what is the name. Sorry, what is the length for this name? So there is a 1 byte here, and here is a type. Okay, so like directory or not directory, something like that. So there's also another 1 byte, and then following on, we will put the name inside this directory. So usually we'll align the size of the name to the 4 byte. And actually we can have the maximum 255 byte here. Okay, so your name can be up to 255 bytes. Okay, maybe you have one question is about why not 256, right? Because 256 can be aligned with 4 byte, but 255 cannot. So the reason for 255 here is because this example, like I targeted on, is on ext4, and because ext4 is a quite recent file system, and for the prior version, like ext2, this kind of version, actually they limited the maximum length to the 255 byte. So it is about for the compatibility. So for ext4, we can only use 255 byte. Okay, but if now you really store a file and the name is in the 255 byte, then ext4 file system will help to pad 1 byte. Will have to pad like 0 data here to make the name to align with the 4 byte. So actually ext4 will help you to pad to 256 byte here. Okay, but according to the compatibility, you can still only use up to 255 bytes. Okay, but the problem is here, like the dirty entries will keep going on if there are new dirty entries comes, right? Okay, but if we directly modify the name, and if the name is larger than the prior one, so it means like if you directly update it, we will overwrite the other dirty entries, and it causes an error here. Okay, because you directly modify it, and the name here is already maybe, for example, it's 4 byte, but maybe after you update the name, it becomes like 8 bytes. So 8 bytes will become so large, and then we'll overwrite the neighbor dirty entries. Then it causes an error. So this is another reason why we don't really update the name in the dirty entry. So if you create a new one, then you just need to mark the prior one as an invalid. Then we can avoid this kind of overwriting neighboring issues. Okay, so this is an example to let you know about how rename happens and what issues will you face about if you directly update the name inside the dirty entries. Okay, so this is for it. Questions? Okay, no questions. Okay. Second example is about the next one is about to let you know about how to access a file path. So usually a user process will request a file like this kind of format. I'm going to get the data from /path/to/file. Okay. So but how system process this kind of stuff? So step 1, VFS parse to get /path/to/file or components. Okay. And then VFS will start to resolve the path for each component. The first step is to check whether the entry of the component is 16 or not. Okay, because like this, if the D entry, sorry, I think this one can be better. So if the D entry is already in the memory, then we can use their inode pointer to get the inode object and inode the data pointer to get the data in the patch cache. Then we are finished, right? So it will be super fast. Okay, but the thing is about if not, okay. If not, then VFS will call the inode operations, the lookup operation in inode to search path inode from disk and create the entry. So this search path inode from disk, actually there are two parts. The first one is to let you know is here. This is the lookup. Oh, sorry, this is not a lookup function. Okay, here, sorry. The second build here, this is the lookup function. So inode will call this lookup function to get where is the data. And then because according to our example, we say we will search the path inode from the disk. So either this. Oh, sorry. One thing to let you know. The root directory inode is always preloaded during the system build. So this one will already be inside the memory. So for the root, we can always skip it. So the second one will be path. So this is the reason why we say to search path, not search root. So for the path inode, what we are going to use is like this. Here, when we are going to search the inode from the disk, we will usually follow this structure, like to get the checkpoint region and then to get the inode map and get inode, and we can get the data inside the data block. So either this is a derivative block or data block, we can use this flow to get the data. Okay, so this one is if the not pass. If this is not, then we'll do this kind of stuff. Okay, so we will recursively run the lookup function to resolve to and file. So at the end, we can know, okay, where is the direction of the file? Okay, so using this, first we will search for the root, and because root already in the memory, so we will use the inode for the root to point to the data block, to point to the data block, and because the data block stores the directory entries, so inside the directory, there should be a path. So reading out the path, then we'll do the same things. We will check about if the path, if the entry of the path is already in the memory or not. If it is there, then we can use the entry to find the inode number, to find the inode object, and inode object can find the data. But if not, then we will run this kind of operation, lookup operation, to search the inode from the disk. So either it is in the memory or it will be on the disk. Okay, so doing this in a loop, then we can finally get where is the data. Okay, so this is about how to put those kind of inode, the entry, and VFS operation together to access the data from the storage device or memory. Okay, so actually, there's one missing pieces that I did not really point out in the prior, is the file object, because I think actually the file object is not quite important, so I just give you a very rough concept about the entry and inode first. So the last one, because we say VFS, there are 4 components. The last one will be the file objects. So it represents a file opened by a process. So there may have multiple file objects for the same file, but each file has only one inode and one D entry. Okay, so file is the concept related to the process, because multiple processes can open the same file. So it is possible to have several files, just like the file descriptor layer. But inode and D entry, you always have one. Okay. And like the D entry object, the file object does not correspond to any on-disk data, because this data structure is corresponding to the process. So it is not really related to the inode, the data on the storage device. So when we are going to update the data, we always will link back to the inode object, and then we will modify the data on the disk like this. Okay, so like file system can implement unique functions for each of those operations, or they can use a generic method if one exists. Okay, so here are several hook points like read, write, asynchronous I/O read, asynchronous I/O write. So actually, most of the file system that support this kind of function. So this function will be hooked to the implementation of different kind of file systems. Then we can, the programmer can call the VFS, and then the VFS will help to translate to the corresponding file system stuff. So this, for example, let's read things like it read count bytes from the given file at position offset into the buffer. So the offset is the offset you here in the open file table. Sorry, it's here. And the offset is here. So there are a very similar concept to think together. Okay. Okay, but I think details are not quite important. Just need to know like each process has their own file object, but actually, no matter how many processes to share the same file, actually they only have one inode. Okay. So if we quickly put the file system components all together, then you can see like this. If you still remember, each process has their own text structure. Because text structure is like process control block. And inside the text structure, actually there is a field. If you go back to our, I think it's lecture 1, something like that, like there is a field called files. And actually using the files, you can get a file descriptor table, and you can get your corresponding file descriptor for the file you are going to access for that process. So this is a file descriptor table, and like for any file descriptor, like we will point to the file. So this is the file object. So here are several fields here. So inside the file object, actually there are two things. It points to the file inode and also point to the D entry. So for the file object, actually we can get the D entry and the inode here. So those are all data structure inside the memory. Okay. And also there is a mount things, like the mount thing is about to describe this file is stored on which file systems. So this is a VFS mount. So to tell you about like where is a super block you need to find to get a file. And also super block, actually, we need a path to know where the super block is. So there is a D entry stuff here. Okay, so this is just a like very brief architecture about that you know the file system where they put together. The virtual file system will look like this kind of stuff. Okay, so still have some time. Let me move to the patch cache. So one more time, back to this figure. Actually, we already learned about the block IO layer, those kind of stuff, and virtual file system we have. And actually, FS specific, you can think about this is the log structure file system part it is. But actually, different file system here, they will have different implementation, but we skip this part. So we'll move on to this one, patch cache, because this one is quite important. When you are going to read the data block from the storage to a memory, you should put into the patch cache. Okay, so the maintenance for patch cache is quite important. So a patch cache is a disk cache. It is going to minimize the disk I/O by storing data in the main memory. Okay, so this is the file in the storage device, and then this is the memory. So in current Linux systems, the memory is managed by the patch label, right? But in storage, actually, it is about the block label. So there is a translation between the block and the file. So actually, this makes the patch cache becomes a little bit complex in the Linux code because like in the memory, we should use patch to manage, but in the storage, it is not about patch. Usually, it's about a file and a blocks. Okay. So like this is the patch cache, and then for the read operations, so you can think about if there is a user process and we are going to read the data out. So the same things like if the user process send the read operations to the systems, then we need to call the system call because we are going to access the storage device. So for any operation, we are going to touch the storage device, access the storage device, we should always call the system call. Okay, so system call CPU will jump into the kernel mode to execute the kernel function. Is about check patch cache. Okay, so with using the check patch cache, CPU can also use a read patch. Okay, so it means like actually CPU will, in most cases, CPU will first check the patch cache. unless you say you don't need to check the patch cache, but or in most cases, CPU will first check the patch cache because it is faster. So if it is hit in a patch cache, then data is in the patch cache. Okay. Oh, one more thing is about actually this patch cache is different from CPU cache. I mean, there are several very similar things because the people were talking about like ARU or like how to replacement, this kind of stuff. CPU cache is a hardware cache. So we use a hardware, we use a circuit to implement this cache. But patch cache is a software cache. You use a program to write this patch cache. So this is very different. Okay. CPU cache should be super fast because it is inside the CPU. So if CPU cache, I mean, if the operation of CPU cache is too slow, then CPU will stall there to wait for the cache to read the data. So CPU cache, the implementation of CPU cache should be not too complex, or for sure, it should be simple. Otherwise, if the circuit is so complex, then CPU should wait there for a lot of time. On the other hand, patch cache is a software solution. So usually it doesn't need to be so efficient like the CPU cache. So for patch cache, you can have more management, more control inside. Okay, so this is a difference between like the cache, because actually there are a ton of cache in the computer system. There are CPU cache, there are patch cache. Inside the storage device, there are also the buffer cache. And then in the storage device itself, there are also another cache. So there are all different kind of cache, but it depends on where the cache is in and how the cache is implemented. Is it a hardware cache or is it a software cache? Okay. So if it is cache miss, then data is not in a patch cache. Then it means like the data should be in the storage device. So we'll read out data from the storage device. Okay. So when we are saying like we are going to move the data from storage device to the patch cache, we will say like we are going to populate the data. So it's just kind of a terminology. I think it's not quite important. And then if we are going to write back the data from the memory to the storage, we call it evictions. So eviction is going to remove the patch from the cache to make room for more patch cache, because usually patch cache will eat up the memory. So the more patch cache, the larger it is, then you will need to sacrifice more kind of memory. So one interesting thing is about like patch cache is only for the file data. So if you still remember when we talk about the process, right? We have like heap, we have stack, those kind of things. Heap and stack, they also use the same memory. So if you have too large of the patch cache, so you will squeeze the room for like heap, okay? Because they are sharing the same memory. So the larger a patch cache is, you cannot use, for example, like mmap if you use too many, or if you use the memory allocation function, those for the heap usage, you cannot use too many because your patch cache is so large. Okay, so the size of patch cache is also one important thing. Okay, so to make room, actually, there's a way called ARU. I think you guys already know about it. And actually in Linux doesn't use the ARU. And ARU, you can think about ARU is a concept. And if you are going to realize the ARU implementation, it will be time consuming. So usually, no matter in CPU cache or patch cache, they don't use ARU. They use like pseudo ARU. Pseudo ARU means like their implementation is very similar to ARU, but it doesn't strictly the same as ARU. So this is the reason why in CPU we use like set associative, this kind of cache design. And in patch cache, we use Linux 2 this design. So they are all very similar to ARU, but not exactly the same, because if you are going to use this ARU to implement them, it will be time consuming. Okay, so I think maybe we can stop here and then let's come back next week.